Colloids. A colloid or a colloidal dispersion is in some ways similar to a solution, and yet it's different. It's a mixture like solution is, but the dispersed substance is something that's very finely dissolved in a dispersing medium. The difference is that it's not, the particles are larger, really, is what the difference is. So here, colloidal particles are usually 1 nanometer to about 1,000 nanometers in diameter. That's much larger than ions, which we usually measure in picometers. Colloidal particles are small enough to stay suspended. They will not settle out. A suspension, chocolate milk is a suspension. The chocolate particles are suspended in the milk, but if you let it sit, they'll settle out due to gravity. A colloid or a colloidal dispersion will not settle out because of gravity. The particles are small enough to stay suspended, but they're larger than solution particles. Under a microscope, and these particles are large enough that they can be seen under a microscope, we see this distinctive jittery motion. So you can imagine here's this molecule, or this particle really, and it moves in these little jerky, seemingly very random directions. You go, this is called Brownian motion, and it's caused by collisions between the particle and molecules in the liquid. Brownian motion occurs in gases as well. We can make a dispersion, we can make a colloid dispersion with soap in water. We've talked about soap before. Here's a soap molecule. It's got an ionic head and this nonpolar tail. And these will form little spheres called micelles. And they will be suspended in the water because of the electrostatic repulsions between the different micelles. You can also form colloids with macromolecules. Those are just really big molecules. Proteins are macromolecules. DNA is a macromolecule.
When it gives types of colloidal dispersion, for example, why is opal used?
We'll get to that right now. So that's a good question. Let's start at the bottom then. So this is an opal. An opal is a dispersion, a colloid of water in glass. And the water is in small particles within the glass. It's not like a hydrate where there's a particular number of particles, but the water is distributed or dispersed throughout the glass. Remember, silicate, it was silicon and oxygen bonded together, right? And so you can have this liquid dispersed in a solid.
So if you break it up, it's not going to feel wet, though, right?
No, it's not going to feel wet. Because there's this very small quantities of water, very finely dispersed.
Is that why it's such a weak substance, though? Is because
it would be weaker than pure silica, right? And it could probably be damaged by heat. I would imagine that if you got it hot, that the water would expand and it could break the opal, or at the very least escape from the opal and discolor it, cause it to look differently. I don't know.
Pure silicate, is that just glass?
Well, the glass that we're familiar with is generally silicate with other things in it. There's borosilicate glass that has boron in it. And they add other things in it to change its physical properties and optical properties. But yes, silicate would be a glass. So we're more familiar with these other types of colloidal dispersions. Whipped cream, that's a tasty one, right? This has air bubbles in the fat of the cream, and they're dispersed. So that's a gas in a liquid. Milk, if you have raw, untreated cow's milk and you let it stand, the fat will rise to the top. That's the cream. And if you skim that off the top, then what you have left is skim milk, and there won't be any fat in there. So what they do is they homogenize the milk. It undergoes a process to make those fat particles disperse better within the milk. And so like whole milk, like what we made our ice cream out of, you know, that could sit in the refrigerator for 2 days, and you go in there and the fat hasn't risen to the top. It's dispersed. It's a colloidal dispersion. Smoke in the air is fine particles of ash that are suspended in the air. And the smoke doesn't just settle out like a cloud of dust will. You know, you get a big dust cloud because the tractor went down the row, and the dust will settle down after a while, but the smoke will just kind of stay suspended. And aerosols are also dispersions. So we're familiar with aerosol cans, right? You shake them up and then you spray, and it sends out this very fine mist. And fog is also a dispersion. The water droplets don't just fall like rain because they're small enough to be suspended. Interesting thing about colloidal dispersions is called the Tyndall effect. And this can be used to test a mixture to see, is this a solution or is this a colloid? Because looking at these two mixtures, they are both clear. Many colloids are not transparent. They're opaque. There's enough particles in there that they block light from going through. But you can have dispersions that are actually clear, transparent. But if you take a beam of light and shine it through a colloid, the particles are large enough to scatter light, and so you see the beam of light. This other container is a solution. The particles here are smaller. They're not large enough to scatter the light, and so you don't see the beam of light. So this is what's going on. This happens in my front hall a lot. My front hall does not look anywhere that grand. It's just very shabby in comparison. But we do have a window, and the sunbeams come in, right? And there's dust. And the dust is in the air, and it's floating around, right? And the light comes through, and you see the sunbeam. Why do you see the sunbeam, and you don't see it over here? But there's dust, and the dust is diffracting the light and reflecting the light.